Oh, okay, accept. So I was saying that it's a busy time with teaching, and so I present something that it's about the work of some years ago, before the pandemic. Anyway, thank you very much for the invitation. I put together several slides, actually. There are also other slides after this about my joint paper with Raymond on non-paid. And we will see if we can cover all of them. I don't think so, but we can stop anywhere it is convenient. So thanks again, and let's start. This talk is about the definition of hyperbolicity, which is the most important property of causality theory. And this property has passed through several types of definitions. And there were some improvements in the last years, particularly looking at low regularity generalization, and this I will also mention. But already in the smooth setting, that there were improvements. Some improvements were even a little surprising. So we are going to talk about those. As I said, this is joint work with Raymond on non-paid, who is a talented mathematician from Benin, the Université d'Abomey Calavi. He did his PhD recently, and his advisors were Cyriaca Tindombe and Manuel Gutierrez, mostly on null geometry and causality of space-time. He also spent 3 months in Florence, and we worked together. And we have still an ongoing collaboration. So our objective in these first slides will be to simplify the definition of global hyperbolicity and causal simplicity. In regular, by regular I mean C11 or C2 metrics, but also in less regular theory that have become fashionable. Also, I will say something more with respect to the paper about these less regular theories. So, as a start, the space-time is a connected time-oriented Lorentzian manifold, whose metric is C2, but C11 will be enough because C11 guarantees uniqueness and the existence of geodesics and of the usual signature. P less than Q means that there is a causal curve connecting P and Q. P is less equal than Q means that they are causally connected or at the same point. P less than Q means that there is a time-lag curve between them. Now we started using with Sanchez 15 years ago already this relation as subset of times M, that is product of space-time by itself, as a relation should be understood. But this was not so usual before, but it's really convenient, as we shall see. In notebooks, you find most use these pointed versions. So a causal diamond is just the causal future of a point intersected with the past of another point. And sorry, what's going on here? Oh, okay. While the causally convex hull of a set that will be important for us is the analog, but with the set in place of the point. So this is the set, is the union of all the curves that start from a set and reach the same set. Now, time-like curves can be deformed remaining time-like, and as a consequence, one can show that the chronological relation is open. Actually, we can show here, we are in the smooth setting. I will mention when we pass to the less regular setting. Moreover, the closure of the chronological relation and of the causal relation coincide, but the causal relation is not closed in general. Simple, for instance, to see this, removing a point from Minkowski spacetime. Then P and Q in this figure belong to the closure of the causal relation, but are not themselves causally connected. This lack of closure of the causal relation is really at the origin of many causal pathologies. And here are some of them. For instance, if I have a closed timeline curves, I'm in a non-chronological spacetime. If I have a closed causal curves, I'm in a non-causal spacetime. But even if there are no closed causal curves, I can have curves that return very closely to the starting point. So this would be a non-distinguishing spacetime. Or even there can be curves that start closely to one point and return closely to the same points. These are no stronger causal spacetime. So this leads to the introduction of a hierarchy of stronger conditions. And of these conditions, some of these conditions are the best ones, so to say, the more convenient. One is causality, another is stable causality, another one is global hyperbolicity that we are talking about. But we shall also be concerned with other properties that do not fall in these kind of properties introduced to remove almost closed causal curves. These other properties are related to properties of the causal relations and have to do with how information propagates on spacetime. So one of these properties is the reflectivity of the spacetime, which is this topological property here. If a point belongs to the closure of the causal future of the point P, then P belongs to the closure of the causal past of Q, kind of time symmetric condition. And they pointed out that there is a ladder of conditions that is independent from the causal ladder, which is this one. The compactness of the causal diamonds implies that the causal relation is closed. This implies reflectivity, and this implies the transitivity of the closure of the causal relation. So for this property, you can also check this review about the smooth setting. So here is a picture of what is going on. We have on the right a ladder of causality condition. At the top, we have global hyperbolicity. Just below it, we have causal simplicity. We should be particularly concerned with these two properties. And then we have many weaker properties, and at the bottom, we have causality. And even below that, we could have chronology, absence of timeline curves. Causality is absence of closed causal curves. And global hyperbolicity, we shall see what is the definition to be used. Here, there is this chain of implication to the left, which is the transverse ladder. And then there are these arrows that go to the top, which are definitions, basically. So global hyperbolicity can be defined in the smooth setting as compactness of the causal emeralds, for instance, and causality. Well, actually, here you can read causal diamonds, those that we introduced before in the smooth setting. It's okay. So we shall return to it. So let us see these traditional definitions. The first traditional definition, well, the first one was about compactness of the space of connecting causal curves, but it's not used in causality theory very much. Instead, we use the traditional definition in causality is this one. Spacetime is globally hyperbolic if it's strongly causal, the causal diamonds are compact. So the future of a point intersected with the past of a point must give a compact set. Causal simplicity is instead a spacetime is distinguishing. I do not enter very much on it. It just means that you cannot start from a point and return very close to that point. And for every point P, these two sets, the future and past over points, are closed. Now, in reality, the first improvement was given by Bernard and Sanchez, who showed that here we had strong causality, which was the condition that you have causally convex neighborhoods. That is, if you leave a neighborhood of the point, you cannot return to the same neighborhood. There are neighborhoods with these properties. But this condition could be improved in this way, just causality. That is, just demanding that there are no closed causal curves. And the same for causal simplicity. For this reason, I will not be much concerned about what is strong causality, what is distinction, because this property will not be used in this talk. So let's. However, in this formulation beta, that is the closure of the causal future of the point, the closure of the path of the point, this condition, and this set are closed, is actually equivalent to many other conditions. And the most important is the first one, that is the relation is closed itself. This is really the most natural condition that you should use, and I will return to it. This is the property that is found in textbooks, as we have seen. That the condition is for every compact set, the future of the compact set or its past are closed. Also, we have this equivalent condition, the causal diamonds are closed, which is less known. This is, instead of asking that the future or the past of a point are closed, you can just ask that the diamonds are closed. But we can also add to this list this property: the causally convex hull of a compact set is closed. It is, if you take a compact set and you take the union of the causal curves that start and end at the same compact set, this set is going to be closed. And all these are equivalent. Also, we have this result that, so why I'm going to insist with these two properties. The convex hull of a compact set is closed. This will be important because this is what survives in low regularity. So that's why we insert it here. Now, we have also this proposition: the closedness of causal diamonds is equivalent to the closedness of these causally convex hulls of compact sets. That is, if you assume that the causal diamonds are compact, you also get that the causal hull of the compact set, the union of the causal curves that start and end at the compact set, is closed, and the other way around. And also with compactness instead of closure. We have also this result. This is still in a regular setting. We should see what changes in a non-regular setting. So these are the equivalent definition that can be introduced for a global hyperbolic spacetime in a smooth setting, or C2, C11. The first is Bernard and Sanchez definition, which is the weakening, where here you have causality instead of strong causality. These are the two properties: non-total imprisonment and the causal diamonds are relatively compact instead of compact, is also equivalent. This is something I introduced in 2007, and this definition is useful to show that global hyperbolicity is stable. That is, if you enlarge or shrink the cones, global hyperbolicity is preserved. The proof passes through this property, not through this one. The reason is that this condition, demanding that this intersection is compact, means demanding that the set is closed. When you change the cones, this property is very hard to prove. You cannot prove, it's not stable. You cannot prove closure when you shrink the cones. Instead, this property is immediate. Because if you have a causal diamond and you shrink the cone, the causal diamond you get might be non-closed, but certainly if you take the closure, it's going to be contained in the previous diamond, the previous closure of the previous diamond that was compact. So the closure remains compact. Okay. That is, this property here makes it obvious that if you shrink the cones, the global hyperbolicity is preserved. Okay, it doesn't make it obvious that if you enlarge the cones, you preserve global hyperbolicity. That is a much harder result, but it's also true. Now, the definition 3 is related to the Seifert relation. The Seifert relation is important because its antisymmetry is equivalent to stable causality. The idea that if you enlarge the cones, you do not introduce closed causal curves. That is, you have a small enlargements of the cones, widening of the cones that does introduce closed causal curves. So this relation is very important. It's closed, it's antisymmetric in stable causal spacetime. So if you assume stable causality, you are assuming that this relation is antisymmetric. It's also closed. And demanding that the diamonds are compact is equivalent to global hyperbolicity. This then is a useful definition because it works with a closed relation, which is important. The fourth definition is what interests most to people that work in PD. There exists a Cauchy-Appel circles. All these are equivalent, and well known to be equivalent. Actually, we can add to this list these other property. Causality and the causally convex hull of compact sets are compact. Similarly, causal simplicity is characterized by causality and the causally convex hull of compact sets are closed. Okay. Actually, for instance, Stefan Sur worked with Bernard, introduced a similar definition, but here they use two different compact sets. We shall talk about that definition that is relevant in the law setting. So in fact, let's go to law regularity. So law regularity it's important in the last year. There is a lot of works on this because it relates to quantum gravity. It's believed to relate to quantum gravity. We believe that the space-time is not a smooth manifold. And so we started investigating what happens if we generalize the usual smooth setting. To start with, one can keep the smooth manifold and just generalize, decrease the regularity of the metric. Now, the Lorentzian metric gives a distribution of cones, and so we start looking at distribution of cones instead of metrics. We could work with C0 metrics. This still gives rise to distribution of cones, but investigation in this direction has shown that it's not very convenient to work with C0 metric because all the results pass to distribution of cones, which are even more general. So basically, the mathematics, when you identify the right concepts, there is this Poria principle, right, that I used to follow. That is, you have to reduce the assumptions, because the less the assumption, the less you can do. The less you can do, the most likely what you do is correct and significant. So we decrease the assumptions as much as we can. And as started out from the work by Fatih Sikonolfi, Bernard Sur, that particularly important is this framework of closed constructions. We practice at every point, you have a closed cone, which is sharp, that is, there is no line passing through the region belonging entirely to the cone. This means that the speed of light is not infinite in any direction. Some call sharp cones pointed cones. It's convex. And we ask that the union of these cones, which is a subset of the tangent bundle, is closed in the topology of the tangent bundle. But we remove the zero because these cones do not have the zero in them. Okay, this is a technical, not very important point. Turns out that to ask a disclosure of this cone distribution, this conic subset of the tangent bundle, is equivalent to say that this map that sends the point to the cone that is interpreted as the future causal cone, this map is upper semi-continuous. It's the same thing, in the sense upper semi-continuity in a suitable topological sense. And this setting preserves many results of causality theory, including the validity of the causal later, limit curve theorems, results on time function, and more. And it even includes the case of C0 matrix, Lorentzian matrix, that gives C0 distribution of cones, but even C0 vector fields. So we are really in a very general framework, where the cone shrinks so much that it becomes a line, an half line, and so a vector field, basically. Okay, but you cannot do everything with closed construction, because sometimes you need that the cones are open. Okay, so you want the cones to have an interior. This is useful when you want to introduce the chronological relation, and you want the chronological relation to be an open relation. And then you ask that if you take the interior of this cone distribution of the drift tangent bundle, this gives a subset of the tangent bundle, which is open in the topology of tangent bundle. And then you take the fiber at every point, at a point or at any point, and you should get something that is non-empty. This means that the cone has interior. And okay, this is called proper construction, and it includes the case of C0 Lorentzian metric, Lorentz-Fields theory, and many other theories, but still on a smooth manifold. Now, with the proper construction, you have a meaningful chronological relation, but it's not true that if you compose a time-lag curve and the causal curve, you can deform to get a time-lag curve. This is expressed by this relation. If you compose causality with chronology or chronology with causality, you get two endpoints that belongs to chronology, that chronologically related. This is not true. And also geodesics that you can define as achronal curves, as curves such that no two points are chronologically related. Geodesics can be defined this way, but they can branch. So what is the general philosophy of this low differentiability investigation? The idea is to identify definitions that are robust, that survive under low differentiability, and to identify the concepts that are the most important at the most fundamental level. Because then we believe that those concepts will be important in quantum gravity perspective. That's why we want to lower all the conditions of causality theory, because maybe the Einstein equations, as we know them, will not survive. But it's very likely that causality will survive even in quantum gravity, even though there are proposals of looking at causality itself as a quantum phenomenon. I believe that causality will still make sense at the quantum level, but maybe, but almost certainly the method will not be smooth. There will be something else. So, for instance, in the smooth setting, we can do many things. We can work, for instance, with two relations: the chronological relation, which is open, the causal relation, which has problem because it might be not closed. But this is too much mathematical stuff. We want to remove objects that are unnecessary. So we want to understand what are the true meaningful concepts that to be used. In my opinion, this work shows that closed relations, for instance, are more important than open relations. Because the work in low regularity, in particular in closed cone structure, has shown that you can reproduce all results of causality theory, almost all of them, the whole causal ladder, just without the chronological relation. But we will comment that. So, in a proper cone structure, which is the structure in which the cones are open, that is, or better said, have an interior, all the definition we gave of global hyperbolicity are equivalent. Nothing changes. Even if the metric is zero, so, or if you work with the Lorentz-Finzer type of structure in which the cones are not isotropic. A causal cone is isotropic if when you cut it with the transverse plane, you get an ellipsoid. It is non-isotropic if cutting it with the transverse plane gives you something that is not an ellipsoid, so you cannot find coordinates in which the cones appears to be round. This means that the speed of light might be non-isotropic. In all these type of structures, those definitions are all equivalent. But if you go to a closed causal cone structure, closed cone structure, then 3 to 5 are correct. The other are not the correct ones. So let me go back. One, which is Bernal and Sanchez, cannot be used in low regularity. Okay. And also 3 cannot be used in low regularity. Why one can say, okay, but why not? Why I cannot use another? But because you want the causal ladder to be preserved, you want a number of properties to be preserved, so you want to choose the right definition that gives you most result, that preserves most results. You see that what you want is that there still be a Cauchy per surface. So this definition here is more appropriate than the first one. You have to ask that the convex hull of compact set is compact, not that the causal diamonds are compact. This is too little, too weak, when you go in low regularity. So 5 is interesting because it means the operation of taking the causally convex hull preserves compactness. And this operation of taking the convex hull is quite natural. In fact, I worked for some years on the theory of topological ordered spaces that was introduced by Natby, a Brazilian mathematician, in the 50s. This is a theory very important that we talk. I don't think I will have much time to talk about it, but it's very important because it shows that most of topology can be generalized to include order. And I promoted, let's say, the application of this body of topological knowledge in relativity. I myself applied it several times. So in the concept of topological ordered spaces, I suggested that in fact, this should be the definition of global hyperbolicity. In this very general concept of topological spaces with an order. Okay, so in relativity, the order follows from the notion of causal curve, but we can just work with the order without the notion of causal curve and just make sense of global hyperbolicity. This is the idea. So the most possible abstract setting is that of topological ordered spaces. Then in the last year, we lowered differentiability conditions. So we started studying C11 metric, C0 metric, C0 configs. For instance, Patienza and Conolfi were the first to study global hyperbolicity for C0 configs. Then someone studied continuous Lorentzian metric and showing the equivalence with Cauchy-Shepard surface. And then Bernard and Sur studied closed structure and imposed this condition here that if you take the future of a compact set and the past of the other compact set, you get something compact. So they based global hyperbolicity on this property. What we are saying is that you can actually use the same compact set here. And so by doing, why this is important? Because by doing so, you return to the general definition I gave for topological ordered spaces. You return to you become compatible with that setting that was already observed before these last studies. So this can be done, and I should say so that, for instance, I don't think that I will be so much time to spend in the last slide I prepared. So let me anticipate about this topic about low regularity. That in the work by Mondino and Sur and Cavalletti and Mondino, they define two notions of global hyperbolicity. They call global hyperbolic the definition by Bernard and Sanchez, basically. And kappa global hyperbolic, the definition, non-total imprisonment plus this condition here that they call causal emerald are compact. I think that we can just not call kappa global hyperbolicity, but just global hyperbolicity, because this should really be the same. Because, as I said, we should not define the definition by Bernard and Sanchez as global hyperbolicity in low regularity. This is not to work. This just does not work. Already for closed structures does not work. So when we go to study optimal transport or Lorentzian length spaces, that for sure is not the definition to use. Instead, we must use this property that the causally converse are preserve compactness. Okay. So now let me return to the smooth setting and to the result with Raymond, because what we showed is that we can remove causality from the definition by Bernard and Sanchez. We shall need non-branching geodesic. That's why we need the method to BC2. In principle, these results can also hold for Lorentzian next spaces that are really under low regular spaces, provided you impose some sectional curvature conditions that guarantee non-branching. So the theorem is a non-compact or non-totally vicious space-time and of dimension larger than 3 is globally hyperbolic if the causal diamonds are compact. So with respect to Bernard and Sanchez, we don't have the assumption of causality. But the dimension is demanded to be larger than 3, but this is okay because our space-time is 4-dimensional, and to be non-compact. But this is also quite okay because it can be shown that in a compact space-time, well, very strange thing happens. You have closed time-like curves. Physicists don't really believe that we live in a compact space. Instead of non-compact, we can ask non-totally vicious, which means that there is at least one point to which this does not pass a closed time-like curve, which is a very minimal condition. Otherwise, the causality would be trivial of the space-time. Also, let me say that even mathematicians don't study space-time in dimension 2. The reason is that, like geodesics in this space-time don't have conjugate points. That is, they are too trivial, the space-time in dimension 2, even from the mathematical point of view. So the proof, we are now going to give the proof of this result, which was found a bit surprising by many people. Well, this should not be understood as that surprising. Let me explain why. The point is that we are assuming that the causal diamonds are closed. To assume the closure is a strong property. You're not just well, because we are assuming that they are compact, okay? But I was saying, okay, if I were to tell you that the causal diamonds are relatively compact, that is, if you take the closure, then you get something compact, your understanding would be actually the same. You would be, well, okay, that's what we were saying, right? That the causal diamonds live in a finite space of space-time, so that they are compact. No, we're not saying just that. That would be just asking that they are relatively compact. Here you are asking that they are compact, which means that they are closed. And to demand that they are closed means to demand something on the closure property of the causal relation. And that's the key to extract the fact that causality can be removed. Okay, it's still surprising, but there is a reason behind this. So let's start. Non-compact manifold implies non-totally vicious. In fact, if the space-time is non-totally vicious, is totally vicious, this means that every point has a time-like curve passing through it. But there is this Carter equivalence relation. These 2 points are equivalent if there is a time-like curve, closed time-like curve passing through both of them. One can show that the space-time splits in the union of these chronology evaluating sets that are all open. Basically, since the space-time is connected, the union, the space, every point belongs to an open set of chronology violation, but the space-time set itself cannot be the union of chronology violating sets, because otherwise it would be disconnected, basically. So one basically concludes that there is just one chronology, one component of the chronology violating set, that is the chronology violating set which P belongs. And that means that the chronological diamond of the point P is the space-time itself. Basically, you can connect P to any other point with a closed timelike curve. And then this means that the whole space-time is the chronological future or the chronological past of the point. But then the space-time itself is a causal diamond. And so it should be compact by assumption, but this is a contradiction with the fact that it is not compact. Then we have compactness of the causal diamond implies reflectivity. This is an implication in the causal ledger that I showed in the beginning. But I'm not going to enter in the proof, but it's easy. Yeah. Then we have step 3, reflectivity and non-totally vicious implies chronology. This result is a not so well-known result by Clark and Yoshi. And the proof is also easy. Suppose that you have a point in the chronology violating set. Since it's totally vicious, the space-time, either the chronological future is different from the whole manifold or the chronological past. Otherwise, any 2 points would be, you could connect P with any other point with a closed timelike curve. Without so generality, assume the former possibility. This means that the chronological future of P has a boundary, and you can pick a point Q in the boundary. But the boundary, then Q belongs to the closure of the chronological future of P. But now we are assuming reflectivity, and this means that I can revert this property here and get that P is in the closure of the chronological past of Q. Now, P, however, P is in the chronological future of P. And the chronological future of P is open. So, you see, here you have timelike curves that start close to P and reach Q. But there is a whole neighborhood of P that belongs to the chronological future of P. So you can go from P to close to P, and from close to P to Q. Which means that Q is in the chronological future of P, which gives a contradiction. And here we have the main steps. So from the assumption on compact manifolds and compact of the causal diamonds, we arrive at that we have chronology. So now we have chronology and compactness of the causal diamond, and we now use the dimension larger than 3. So we want to get the next steps, that is, go from chronology to causality. So suppose that causality does not hold. Then there is a closed causal curve. But this closed causal curve, by chronology, must be an achronal curve, that is, like geodesic. If it were not like geodesic, it could be deformed in a closed timelike curve, and that would have chronology violation. So this must be a like geodesic, that is in yellow here. Now, if we pick any point of P and Q on this closed like geodesic, and I connect another point R to Q with a time-like curve, obviously I can go from P to R, or with the curve going from P to Q and then from Q to R. This means that if I pick any 2 points in this gamma, actually they have the same chronological future. Because this figure here shows that the chronological future of Q is included in the chronological future of P. Because P is in the past of Q, in the causal past of Q. But actually Q is in the causal past of P, because there is this identification. That is, if you follow Q along gamma, you reach P. And so the roles of P and Q can be exchanged, and so you get that actually this chronological future is the same. So we can speak of chronological future of the curve gamma. But now this chronological future has a boundary, and the boundary is non-empty. It's non-empty because gamma itself belongs to this boundary. Now, this chronological future is what is called a future set. That is, if you pick a point in it and you consider time-like curves starting from there, you still remain in the set. The boundary of this future set are called achronal boundaries in relativity. They are actually hypersurfaces. That might be non-regular, they are typically Lipschitz, but anyway, they are hypersurfaces. And so they cannot be just the curve gamma. There must be another point belonging to the hypersurface, which is in this figure is R, that belongs to this boundary, but not to gamma. And then we pick this point, which is, as we see, in the boundary of the future of Q. But okay, here, by the transverse ladder, we know that by the compactness of causal diamonds, the causal relation is closed. So this point R, which is in the boundary, is actually in the causal future of Q. So this point R, there is a curve beta which is causal from Q to R. But this beta must be okay. The point is that if I consider point P in gamma, I can go from P to Q. Now, beta cannot, if beta is a time-like curve, I can go from P to R with a time-like curve because I can deform these segments. And so R would be in the chronological future of P a contradiction. However, if instead beta is a geodesic, I would have a corner here in Q. So I can conclude the same, because there must be a corner, because if there were no corner, beta would be a prolongation of gamma, and the point R would stay in gamma, where we said that it must stay outside. So the conclusion is that I can go from P to R with the time-like curve, but this is a contradiction, because R belongs to the boundary. So this shows that the assumption that there was a closed causal curve is incorrect. And so we can reach causality with our assumptions. Which is, causality was the assumption in Bernard and Sanchez's definition. So there was no need to put it there. we could remove, as Bernard and Sanchez remove weakened strong causality to causality. We have shown that we can weaken strong causality by removing it completely, just demanding this dimensionality and non-compactness conditions. I can also conclude with, well, the proof by the Bernard and Sanchez can be also be given in this way. Strong causality can be shown to be equivalent to this implication. When you have 2 points P and Q that belongs to the closure of the causal relation and Q and P belongs to the causal relation, then the 2 points are the same. This is strong causality, but the compactness of causal diamonds, the causal relation is closed. So this line here belongs to this line here, which is causality. So these two are equivalent under compactness of the causal diamond, because this implies the closure of the relation. So this is the proof. So in bold are other assumptions. What we did to summarize, we start with the compactness of causal diamonds and the non-compactness of M. We proved that the spacetime is non-totally vicious. Then we use this result by Clark and Joshi that we also proved in this talk. That implies, well, we know that compactness of causal diamond implies reflectivity. Clark and Joshi tells me that non-totally vicious and reflectivity implies chronology. But then the compactness of causal diamonds and dimensional larger than T implies the closure of J. Chronology and dimension larger than 3 implies causality, is the proof we just gave in the previous slide. And the last step is Bernard and Sanchez that is just on causality. So, as I said, I added several slides that I'm not going to talk about. What about the importance of close relations, and particularly, to promote this approach of working with topological ordered spaces and a closed relation, which is the most possible general thing to do, and gives the best definition of our hyperbolicity under regularity. This result, as I said, the possibility of removing causality altogether, is just for the smooth case, for C11 case. You can work with Lorentzian spaces. You see, what is that we used? This is interesting. What is that we used regularity, C2 regularity, or non-branch? Because here we use non-branching. When I said that beta, if beta is a geodesic, and here there is no corner, then R is in gamma. But this is not possible because I took R outside. So beta cannot be a geodesic. Well, if it is geodesic, it's I can reach gamma with n like curve. But these are all these arguments assuming non-branching of geodesics. So it doesn't hold in non-regular theory. But in Lorentzian spaces, it can hold under suitable bounds on the sectional curvature. Okay, while instead in optimal transport version, it's not natural. So, yeah, okay, so I think I will end here. I think meantime. Thank you.
would like to really thank you, Professor Minguzzi, for the very inspiring talk and for all this important information. Anyone who would like to ask any question? Actually, until people ask any question, because I think there is one question by Nicholas Kalogeropoulos. Just to, I mean, the temptation, Professor Minguzzi, to ask you about the connection, if you can tell us of black hole evaporation with.
Yes, you asked. Yes, you asked in the beginning.
Global hyperbolicity, which is really, it's something that you cannot understand easily. I mean, if you don't know. Both.
Okay.
Yes.
Okay. That in that paper, so I published this paper where Penrose's theorem is proved without the assumption of global hyperbolicity. Global hyperbolicity is one key assumption in Penrose's theorem, and actually, some people believe it could not be dropped. It was even written down in Nokia and Davis' book that was a necessary condition. But actually is not. And there was a major physical reason why a weakening should be found. Because the argument was, let me see, the problem is, if you look at the causal structure of an evaporating black hole, this causal structure is not future reflective, but is past reflective, if I remember correctly. That is, it cannot be global hyperbolic. It is not even causally simple, it is not even causally continuous. So all the Penrose diagrams for evaporating black holes stay more or less in the middle of the causal ladder of spacetime. So how can you possibly use global hyperbolicity to prove a singularity theorem for black holes? Because you start from collapsing matter, you assume global hyperbolicity, you obtain that this collapse, that a singularity is going to form. But then if you assume a cosmic censorship, some reasonable physical assumptions, you get that the space-time ultimately is basically a Kerr black hole. But then a Kerr black hole evaporates. But then if it evaporates, it's not globally hyperbolic because evaporating black holes are non-globally hyperbolic. So what's going on here? You started from Penrose's theorem that assumes global hyperbolicity, and you end up with a black hole which is evaporating, which is not globally hyperbolic. There is something wrong. What is wrong? What could be wrong? There are two possibilities. Could be wrong the idea that there is a singularity, because Penrose's theorem assumes is entirely classical, and so it could be that the collapse, if you take into account quantum mechanics, does not lead to a singularity. And that will explain that you cannot join the conclusion of classical general relativity that predicts a singularity with those of quantum mechanics that predicts evaporation. If you join them, you get a contradiction. You start from global hyperbolicity and you end up with something that is not global hyperbolic. The contradiction is that you are merging two theories that don't work. So basically, that would point out that there is no singularity actually, and that Penrose's theorem is wrong in a quantum context. The other possibility is that no, Penrose's theorem can be saved because global hyperbolicity is not needed to infer the singularity of the black hole. And in fact, this is what happens. You can even infer that there is the singularity, even if there is chronology variation. as long as you have this property of past reflectivity, which does not belong to the causal ladder, belongs to the transverse ladder, belongs to the way information propagates on spacetime. So that's what is the connection? Well, the connection is that in that theorem, basically you drop global hyperbolicity altogether, so you don't even need the definition actually. In a sense, what you need is predictability. You do not need retrodiction. Okay, this is something I was asked also in a philosophical department where people are concerned about this type of distinction. That is, global hyperbolicity is determinism. Determinism in the future and determinism in the past. I can recover the space-time even starting from a Cauchy surface to the future, but also to the past. Instead, here, the theorem of the existence of a singularity can be proved even if you go in only in the forward direction. You don't need the past direction, and you need even less than that to actually. But that explains that global hyperbolicity can be much weakened in these singularity theorems. But yes, I mean, I'm happy that global hyperbolicity, because you see, from the point of view of somebody working in causality, we are interested in all many aspects of causality evaluation. The Einstein equations tells you that they exist. But if you are a PhD theorist, you always start from a global hypersurface, a Cauchy hypersurface. You develop your space-time, and your space-time is always global hyperbolic by definition, because you develop from there. That is, if you develop with a PDE, you only get the global hyperbolic part of the space-time. While we are looking from the space-time as a whole, so we study violation of causality, all these pathologies, in a sense, because we believe that they actually can exist.
Thank you very much for the explanation, Professor Minguzzi. Nicholas would like to ask a question, if you don't mind.
Well, I think my perspective is slightly more physical, so probably this is not an appropriate question, but if somebody would say something about quantum gravity, right, except for the fact, of course, that we do not know, is that if we look at the relativistic equations, they are multi-particle equations. So the concept of a point in quantum gravity may not even make any sense, in the sense that probably something along the lines of optimal transportation in Lorentzian spaces that Professor Schur and some other people have written papers about, which I have not read yet, but so I don't really vouch for this. But they should be more probably pertinent. Therefore, the concept of global hyperbolicity that you describe, of course, it's a generalization of the one conventionally used, but it may have to be relaxed even more in order to accommodate, and probably non-branching things may also be taken into account. I don't know, probably in a restricted context, we have to maybe redefine limits and stuff like that. So from that, so that's something that's
okay, I understand. Okay, I can answer this comment this way. First, in optimal transport, you have actually geodesics. Okay, optimal transport over a geodesic flow. So you have curves there too. You need to make sense of causal curves there too. In general, and it's the same in also Lorentzian spaces. But causality theory is very robust in the sense that, as I said, the true framework, in my opinion, the one that is really the deepest one, is that of topological ordered spaces, where you have a closed relation, which is causality. There you don't have curves. There you have a relation. And the definition of global hyperbolicity that I gave, that is, the relation is closed, the relation is antisymmetric, and the hull of compact sets is compact, there are no curves here. The nice part is that this definition of global hyperbolicity is the one that I introduced just working in abstract framework of topological things, with this motivation in mind of quantum mechanics anyway. But I started out in recent years, in the last paper, about all these settings, zero metrics, Lorentzian spaces, optimal transport, is actually the one that is used in this guide, but is that definition. So actually, I share your point of view. Ultimately, curves should not be that important because particles should not be that important. What is important is the causal relation, which is a relation. It's a subset of the product, and that's all. And it's an historical accident that we have been led to causality passing from curves. This type of feeling, I started having this type of feelings already in 2007, when I started to work on the Sefer relation, which is a closed relation. We started working with time functions, and we realized that the existence of time function in stably causal spacetimes is related to the fact that there is a closed relation, which is the Sefer relation. The Sefer relation can also be defined as the smallest closed and transitive relation. And you can even define it without using curves, because and what was important to the existence of time function was its closure. That's where I realized that there was this theory by Nackby. I went to Google, so to say. I started, well, my insight was, okay, Hawking constructed the time function using average of widening the cones, very complicated stuff, that you find in Hawking book. But in the end, all this average opening of cones leads to a relation, which is the Sefer relation, which is closed. So my insight was, in my opinion, the existence of time function is related to the existence of this closed relation. That's because it's the analog of the so-called Urison lemma in topology. If you have Hausdorff-ness, you can separate two closed set with a function that is continuous and separate them. So I went to Google, I wrote existence of continuous increasing function closed relation, and I discovered the whole topology work by Nackby. There was somebody else that did that and that applied that in the relativity. So I perfectly agree. It's a very good observation that in the end we need to abstract from curves. In my opinion, the direction is work with relations. Thank you for your comment.
Thank you very much, sir. Thank you.
Very much. Any other question? I think we made you tired, Professor Minguzzi. You're already talking for more than 1 hour. We would like to really thank you, and we would be really happy if you join us in our seminar in the future on campus here in Kuwait. It was a very inspiring talk. It was a great honor to have you here.
Thank you. Thank you very much for your kind invitation.
Thank you very much. Thank you. Greetings to Italy.
Thank you very much to all of you.
Thank you.
Yeah. Bye.
Bye. Bye. Thank you.